Hello learners, welcome to the episode 2 of P block elements. If you recall, we ended our first episode with anomalous behavior of boron. We may take our discussion further with compounds of boron and aluminium and the chemistry of group 14 elements. After this discussion, you will be able to understand the chemistry of compounds of boron including borax, orthoboric acid and diborane. Appreciate the various uses of boron, aluminium and their compounds. Locate the group 14 elements in the modern periodic table. Know the abundance of different elements of group 14. Describe and justify the trend of covalent radius, ionization enthalpy and electronegativity of group 14 elements. Explain the physical properties of the carbon family. Let us start the discussion with the chemistry of borax. Borax is the most important compound of boron. It is a white crystalline solid of formula Na2B4O7 with 10 molecules of water of crystallization. As a matter of fact, it contains the tetranuclear units of borate ions with formula as expressed on the screen. As you can see, borax dissolves in water to give an alkaline solution. Sodium borate, when reacts with water, gives sodium hydroxide and orthoboric acid. When borax is heated, it first loses water molecules and swells up. On further heating, it turns into a transparent liquid which solidifies into glass-like material known as borax bead. You can see the reaction involved in your screen. Sodium borate, when heated, first converts to sodium metaborate and on further heating gives boric anhydride and sodium monoborate. The borax bead test is used to identify transition elements as their metaborates have characteristic color. Dear learners, please perform this test under the supervision of your teacher. Prepare a loop on the one end of platinum wire and heat it to red hot. Dip the red hot loop in borax and heat it again till it forms colorless bead. Then again dip this bead in a test salt and heat till it shows distinct color. The distinct color is characteristic of test salt. It varies from salt to salt. Similarly, when borax is heated in a Bunsen burner flame with cobalt oxide on a loop of platinum wire, a blue colored cobalt borate bead is formed. Next up we have is orthoboric acid. Orthoboric acid, that is H3BO3, is a white crystalline solid with a soapy touch. It is sparingly soluble in water but highly soluble in hot water. One of its preparation includes the acidifying of an aqueous solution of borax. You can refer your screen for the involved reaction. When sodium borate is acidified with aqueous solution of hydrochloric acid, orthoboric acid along with sodium chloride is produced. It can also be prepared by the hydrolysis of most boron compounds like halides, hydrides, etc. Orthoboric acid has a layer structure as shown. In the respective structure, the planar BO3 units are joined by hydrogen bonds. Let me show you the structure of boric acid with the help of a ball and stick model. In this model, the black spherical ball represents the atom of boron. The red spherical ball represents the atom of oxygen and the purple color ball represents the atom of hydrogen. This geometry is planar in nature and the oxygen and hydrogen atoms are used to form hydrogen bonds. Boric acid is not a protonic acid but acts as a weak monobasic Lewis acid by accepting electrons from a hydroxyl ion. When orthoboric acid reacts with water, it produces tetrahydroxyborate ion along with hydronium ion When orthoboric acid is heated above 370 Kelvin, metaboric acid is formed, which on further heating yields boric oxide. The reaction involved is represented on the screen. Other important compound of boron that we need to study is diborane. The simplest boron hydride known is diborane. Diborane is a colorless, highly toxic gas with a boiling point of 180 Kelvin. It catches fire spontaneously under exposure. It burns in oxygen, releasing an enormous amount of energy and forms boron oxide. When diborane reacts with oxygen present in air, gives boron trioxide with water, and the amount of energy released for the combustion of 1 mole of diborane is observed to be 1976 kilojoule per mole. Most of the higher boranes are also spontaneously flammable in air. Preparation of diborane involves treatment of boron trifluoride with lithium aluminium hydride in diethyl ether. Let me explain you the structure of diborane using ball and stick model. In this model, the black spherical ball hydrogen represents boron atom and the red spherical balls represent hydrogen atom. Here, as you can see, the 4 terminal hydrogen atoms and the 2 boron atoms lie in one plane. Above and below this plane, there are 2 bridging hydrogen atoms. These 2 are the bridging atoms. Each boron atom uses sp3 hybrids for bonding. Out of the 4 sp3 hybrids, on each boron atom, 1 is without an electron. The terminal BH bonds are regular 2 center 2 electron bonds, while the 2 bridge BHB bonds, these are the BHB bonds. These 2 bonds are 3 center 2 electron bonds. These are different and can be described in terms of banana bonding. Preparation of diborane involves treatment of boron trifluoride with lithium aluminium hydride in diethyl ether. Reaction is 4BF3 plus 3LiAlH4 giving 2B2H6 plus 3LiF plus 3AlF3. Laboratory preparation of diborane is done by the oxidation of sodium borohydride with iodine represented as 2NaBH4 plus I2 giving B2H6 plus 2NaI plus H2. Whereas industrial scale synthesis involves the reaction of BF3 with sodium hydride, which is 2BF3 plus 6NaH giving B2H6 plus 6NaF. When we move to the chemical properties of diborane, it is observed that boranes are readily hydrolyzed by water to give boric acid. Diborane undergoes cleavage reactions with Lewis base to give borane adducts, that are BH3.L, B2H6 plus 2NeMe3 giving 2BH3.NMe3, B2H6 plus 2CO giving 2BH3.CO. There is coordinate bonding from nitrogen to boron in adducts, as boron having a vacant p orbital is an electron deficient structure and nitrogen having the lone pair is electron rich center. Moreover, when diborane reacts with ammonia, gives initially B2H6.2NH3 and on further heating yields borazine, also known as inorganic benzene, as it resembles with its ring structure with alternate BH and NH groups. It is also aromatic. Although benzene and borazine resemble each other in structure, but still they differ in several chemical properties. The reaction is expressed as 3B2H6 plus 6NH3 giving 2B3N3H6 plus 12H2. Boron also forms a series of hydridoborates. Tetrahydridoborates of several metals are known. Lithium and sodium tetrahydridoborates, also known as borohydrides, are used as reducing agents in organic synthesis. They are useful starting materials for preparing other metal borohydrides. Till now, we have learned about group 13 elements and some of the compounds they form. But we must know that why do we need to study about these? Let us now discuss some of the uses of boron and aluminium and their compounds as well. Boron is a hard refractory solid of high melting point, low density and very low electrical conductivity, thereby finding a variety of applications. Boron fibers are used in making bulletproof vest and light composite material for the aircrafts. The boron-10 isotope has high ability to absorb neutrons, due to which metal borides are used in nuclear industry as protective shields and control rods. Industrial applications of borax and boric acid involves the manufacturing of heat-resistant glasses, glass wool and fiberglass as well. Borax is also used as a flux for soldering metals, for heat, scratch and stain resistant glazed coating to earthen wires, and also as a constituent of medicinal soaps. Aluminium is a bright silvery white metal with high tensile strength. It also has a high electrical and thermal conductivity. Aluminium is used extensively in industry as well as everyday life. Aluminium and its alloys can be given shapes of pipes, tubes, rods, wires, foils, etc. Therefore, used in packaging, utensil making, construction, airplane and transportation industry. However, due to the toxic nature of aluminium and its compounds, its domestic uses have been reduced. That is all we need to learn in class 11th for group 13. Next to this, we may start with group 14 elements, also known as the carbon family. Members of the group 14 include carbon, silicon, germanium, tin, lead and flavorium. When we talk about the abundance, carbon is the 17th most available element by mass in the Earth's crust. In elemental state, it is available as coal, graphite and diamond, whereas in combined state, it is present as metal carbonates, hydrocarbons and carbon dioxide in air. The combination of carbon with other elements provides an astonishing array of materials ranging from living tissues to drugs to the plastics. Our entire organic chemistry is devoted to carbon containing compounds, as it is an essential constituent of all living organisms. Silicon is the second most abundant element on the Earth's crust, present in nature in the form of silica and silicates. It is very important component of ceramics, glass and cement. Germanium exists only in traces. Tin occurs mainly as cassiterite, tin oxide and lead as galena and PBS, whereas flerovium is synthetically prepared radioactive element. We will be discussing the important atomic, physical and chemical properties further. The valence shell electronic configuration of group 14 elements is Ns2Np2, whereas the inner core configuration of elements differs. Covalent radius in the group is expected to increase from carbon to silicon, whereas from silicon to lead small increase is found. This is observed due to the addition of a new energy shell in each succeeding element. The increase in covalent radii from silicon to lead is small due to ineffective shielding of valence electrons by the intervening d and f orbitals. When we talk about the ionization enthalpy, the value of first ionization enthalpy of group 14 is higher than the corresponding members of group 13. Although ionization enthalpy decreases down the group, but a slight increase from a tin to lead is observed as a consequence of poor shielding effect of intervening d and f orbital. Due to the small size, the elements of this group are slightly more electronegative than group 13. Physical properties of group 14 explains that all members are solid, out of which carbon and silicon are non-metal, germanium is a metalloid, whereas tin and lead are soft metals with low melting points. It is observed that melting points and boiling points of group 14 elements are much higher than those of corresponding elements of group 13. To conclude this episode, we shall recall all the discussed concepts. The first one is borax, orthoboric acid and diborane are important compounds of boron, and our session included their physical, chemical properties along with their preparations. Boron is hard refractory solid with high melting point, low density and very low electrical conductivity. Hence, it has various domestic as well as industrial uses. Aluminium is silvery white metal with high tensile strength, with high thermal and electrical conductivity. It also forms alloys and have various industrial and everyday use. Group 14 members include carbon, silicon, germanium, tin, lead and flerovium. Valence shell electronic configuration of group 14 is Ns2Np2. Considerable increase in covalent radius is observed from carbon to silicon due to the presence of completely filled d and f orbitals in heavier members. Ionization enthalpy of group 14 members is slightly higher than that of corresponding group 13 members. As we approach towards the end of this discussion, let me give you some interesting questions to puzzle around. The question number 1 is, why is boric acid considered as a weak acid? Next question is, how will you explain the structure of diborane and boric acid? Third question is, suggest reasons why the BF bond in BF3 is shorter than the BF bond in BF3-4- ion. So learners, that is all for this discussion. We will continue to learn some more about p block elements in other episodes. Till then, thank you.